three parts A, B, C, and D. So going into this problem, part A, I'm given quite a bit of information. I'm giving the integrated form and integrated equations of the radial distribution density, which part A is asking me for. It's asking me to plot this integrated form as a function of distance d. So d will be on my x-axis for elements hydrogen, He+, and lithium 2+. So to solve this, I had to look at each of the variables and see what I knew and what I didn't know. D is the function we are graphing it for, so I knew that would stay as D. Z is atomic number, so for H, He, and Li2+, I had to find the Z values for each of those respectively, and A0 was a constant, which took me forever to find. But to solve that problem, I substituted all of the given information that I knew into each of the equations and graphed them, which is what the question was asking for. It was asking for the graphs. So once I had these equations, by substituting each of those values in, it came up with a graph like this. I used my software of choice as Desmos. And I got each of these graphs for hydrogen, helium+, and lithium 2+. Part B was asking how I interpret each of these lines and how I describe the behavior I see in the graph and how it helps me understand the size of the ions. So essentially what I noticed is that where all of them are 90% probability of being found, it's a much further distance for hydrogen as it is for helium+ and lithium 2+, which means to me that the electron will be found much further away from the nucleus in hydrogen than the other two. Meaning that this function basically shows me the size, essentially, of the ion. Hydrogen being the largest and lithium being the smallest. And yes, so this is how I described it in my homework. Part C asks, if Bat Beyer were to find the size of the sphere, that would give him 90% probability to find the electron. It's asking what size he would want to draw. To solve this problem, it's giving us, essentially, the probability density as 0.9 or 90% probability. To solve this with math, I would put the 0.9 here and solve for D. But none of the calculators, this is a pitfall, none of the calculators would spit out an answer that I was looking for. So I decided to just work smarter rather than harder and graph a line at 0.9 probability and see where it intersects each of my separate functions to find the exact value as to where Bat Beyer would use to draw his little drawings. So for hydrogen, where it intersects at a 0.9 probability, 90% probability of finding the electron at a 1.4 angstrom distance from the nucleus. 0.7 for helium plus and 0.4693 for lithium 2+. This also shows, just going off of part B, that this function gives us the size, because at 90% probability, it's at so much further away from the nucleus for hydrogen than it is for helium and lithium. And so I took these values and gave them to Bat Beyer so he can make his drawing. I converted them to angstroms and picometers because both of those were given in the problem and I wasn't sure exactly which one to use. So explain in my words. Part D is asking me to explain the difference between radial distribution function and probability density. Nothing that I was given there's no solving this problem. It's all understanding of concepts. So to attack this problem, I just had to explain it. And I explained it as a probability density as being the probability to find an electron anywhere, whereas the radial distribution function has a spatial aspect at a certain d distance from the nucleus. Pitfalls I found were not knowing that A0 was a constant. I heard they got that on last year's homework, which is unfair, but it's okay. Another was graphing my thing right, but I found a way to do it just using the print function, the print thing on Desmos. So Thank you so much. Yep, I enjoyed this problem. It really pushed my brain to the limits. I hope you guys have a great time grading the rest of these. And yeah, Chelsea's out.